Hello and welcome to the drug delivery experiment performed by Group 7. It was important that we took safety precautions while performing this experiment. To avoid accidents, necessary personal protective equipment such as gloves, safety goggles, and a lab coat should be worn in the lab at all times. If tartrazine or calcium chloride comes into contact with skin or eyes, rinse under water for 15 minutes. It was also important to dispose of chemicals to their respective waste containers. Any solutions containing tartrazine, calcium chloride, or alginate had to be disposed in a hazardous waste container, while needles and syringes were discarded in a sharps container. The major learning objective of this experiment was to determine the effect of different drug delivery variables on the release of a drug from hydrogel beads. With a dye called tartrazine along with beakers of water, we simulated the release of a drug into the human body. There are two equations that were relevant in analyzing our data. The fraction of dye release, as shown by F equals mt over m infinity, is equal to kt to the power of n. Mt is the mass of the drug release at time t, m infinity is the mass of the drug release at equilibrium, k is the kinetic constant, t is the release time, and n is the diffusion constant. The equation can be rearranged into log f equals n times log t plus log k to solve for the diffusion parameters. Plotting log f versus log t yields a linear function in which the diffusion constant n and kinetic constant k can be determined from the slope and y-intercept, respectively. 3 adjusted variables were chosen for this experiment. Variable number 1 was bath stir rate, and trials were run at 100 rpm, 200 rpm, and 300 rpm. Variable number 2 was the needle size at 16 gauge, 19 gauge, and 22 gauge. Lastly, variable number 3 was the bead cross-linking time, in which trials were run at 2.5 minutes, 5 minutes, and 7.5 minutes.
The first step in this experiment is preparing the solutions. First, measure out a half a gram of tartrazine and add it to 1 liter of deionized water. In a separate container, add 3 grams of alginate to 300 milliliters of the tartrazine solution and shake vigorously. This can be put aside with a stir bar to continuously mix until the next lab period, as it will take a while to fully dissolve. Now, use 500 milliliters of tartrazine solution and approximately 43 grams of calcium dichloride to make a solution that is about 6% calcium dichloride by weight. With the spectrophotometer set to 427 nanometers, zero it first using deionized water, and then measure the absorbance of 4 samples of tartrazine solution of known concentrations, such as 2.5, 5, 10, and 12.5 milligrams per liter. This data will later be used to make the calibration curve. Fill a weigh boat about halfway with calcium dichloride solution. Then, load a syringe with the designated needle size with 3 milliliters of alginate. Holding the tip of the needle above the weigh boat, slowly dispense the alginate into the calcium dichloride dropwise, trying not to let the drops fall on top of one another. Leave the beads in the calcium dichloride for the designated cross-linking time. Once this time is up, pour the contents of the weigh boat into a filter and wash with deionized water. Set up 3 150 milliliter beakers on 3 stir plates, each containing 100 milliliters of deionized water and a stir bar. Set the stir plates to the designated stirring rate. Scrape the beads from the filter paper into the beaker on one of the plates and start the timer. In taking measurements, samples must be taken from the beaker once every 2 minutes for the first 10 minutes, once every 5 minutes for the next 20 minutes, and then once every 10 minutes for the next 30 minutes. To take measurements, Use a Pasteur pipette to draw a small amount of water from the beaker and empty it into a cuvette. Put the cuvette into the spectrophotometer and record the absorbance.
The first thing that was done for the data analysis was to create the calibration curve that would be necessary for graphing the fraction of dye released as a function of time, and by extension, the theoretical model used to solve for n and k. After the calibration curves were made, the recorded absorbance values from the experiment were then averaged and plotted against time, with the error bars representing the standard deviation between the three trials. We then divided the average absorbance by the slope of the calibration curve. This gave us the concentration of the dye in the bath at any given time. This value was then divided by the maximum concentration in the bath, or at time equals 60 minutes, and then graphed these results. From there, the theoretical model, which was described in the theory section, was applied. And by plotting the log of the fraction of dye released as a function of the log of time, we were able to find both the diffusional exponent n and the constant k. The functions were approximated using a linear function, with the diffusional exponent being found by measuring the slope of the line, and the constant found by taking the inverse log of the y-intercept. This was then repeated for the various needle sizes we wanted to test. And then again for cross-linking time. From the linear approximations of the three theoretical models, the following values were obtained. To evaluate the type of diffusion, the diffusional exponent must be compared with other known values. When the value of n is between 0.45 and 0.99, the transport is non-Fickian, or anomalous transport. When n is 1, the transport is zero-order release. And when n is in the order of 0.43, the diffusion is Fickian. With the exception of the 22-gauge needle, the diffusional exponent was consistently lower than 0.43, leading us to believe that the transport was Fickian. It should be noted that the differences between the trials and variables seemed almost random, leading us to believe that adjusting the variables had little impact on the rate of diffusion. This may be because the variables did not have a significant enough of a difference between the values, or the beads not being clean enough, causing errors in the measurement, or some beads bursting before being added to the bath, causing the same type of error. We are, however, confident in our results, as each trial for each experiment followed the same exact trend with similar values. We thank you for your time, and hope you have a wonderful spring break.